Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
Hello and welcome. It is February 6, 2026. I want to start today with a little thought experiment. Just, humor me for a second. I want you to imagine a clock, a simple analog clock on a wall.
Okay, got it.
Now imagine that clock starts to melt. The numbers are dripping down the wall like something out of a surrealist painting. Or maybe the gears inside start spinning so fast they liquefy, or they start going backwards, or somehow exist in two places at the same time.
A quantum clock.
Exactly. Because we are starting today's conversation with a question that it's kept philosophers up at night for centuries and has pushed physicists to the absolute edge. What is time?
It's the big one, isn't it? It is the one constant we all experience, but the one thing nobody can really define. St. Augustine had that famous quote about it.
Oh, right. What was that?
It was something like, "What then is time? If no one asks me, I know. If I wish to explain it to one who asks, I know not." It's just, it's the water we're swimming in, but we can't grab a handful of it.
It feels so absolute to us, day in, day out. But we know from physics, from relativity, that it isn't. It's flexible. And when you go small, really, really small, it gets even stranger.
It really does. It stops being this sort of universal metronome, this background beat for reality, and it becomes a property of the system itself. It becomes a variable.
And that is exactly where we're headed today. We're looking at a pretty incredible breakthrough coming out of EPFL, the École Polytechnique Fédérale de Lausanne over in Switzerland.
A fantastic institution.
They've managed to do something that honestly sounds impossible. They figured out a way to measure time on the smallest possible scale, but, and this is the part that really got me, they discovered that the speed of time actually changes. It depends on the shape of the matter it's in.
Which is a huge deal. Because normally when you bring quantum mechanics into the discussion about time, the problem gets harder, not easier. Time is notoriously slippery in the quantum world.
Right, because we tend to think of quantum events, these little jumps an electron makes, as being instant.
Right.
It's in one place, one energy level, and then poof, it's in another.
Exactly. Like a teleport. We often treat them as instantaneous, partly because the math is a lot cleaner that way, but also because, honestly, measuring any duration has been next to impossible.
It's just too fast to see.
But this new research, it basically pulls back that curtain. It says, no, it's not a magic trick. It's not instantaneous. There is a duration. It's a process. And what's really amazing is that the length of that process is controlled by geometry.
So that's our mission for today. We're going to unpack this whole thing. We're going to figure out how on earth you can clock a quantum event without an actual clock, because using one apparently messes up the whole experiment.
Right.
And then we're going to get into this really mind-bending finding that the symmetry of a material, its actual atomic architecture, can warp how fast time passes for the electrons living inside it.
It's this beautiful place where geometry, quantum theory, and the very philosophy of time all intersect. It really makes you question if time is this fundamental thing flowing everywhere, or if it's more of a local effect, generated by the environment itself.
Okay, so let's get into it. Part 1, the scale and the struggle. Before we talk about timing something, we need to be really clear on what it is. When you say a quantum event, what were the researchers actually measuring?
So they were looking at one of the most fundamental processes in quantum mechanics. It's called a quantum transition. The classic example is the photoelectric effect, which Einstein won his Nobel for.
That's where light hits a metal and knocks an electron out.
Precisely. A photon, which is a particle of light, comes in and smacks into an electron that's bound inside a material. The electron absorbs the energy from that photon, gets super excited, and uses that energy to, make a run for it. It escapes the material entirely.
It's a prison break.
A quantum prison break, yes. It's transitioning from being bound to the material to being a free particle. And the huge question has always been, how long does that take? Is the escape instant? The moment the photon hits, is the electron out? Or is there a delay, a kind of reaction time?
And I'm guessing we're not talking about seconds here, or even nanoseconds.
Oh, not even close. We are operating in the realm of the attosecond.
The attosecond. It's one of those words that sounds fast, just saying it. But help us, get a handle on this. The number 10 to the minus 18 seconds is just It's an abstraction. A decimal point, 17 zeros, then a 1. How do we even begin to visualize that?
It is almost impossible to wrap your head around, you're right. The analogy the researchers from EPFL use is probably the best one I've heard.
Okay, lay it on us.
All right. Think about light, the fastest thing there is. It travels at about 300,000 kilometers per second. It can zip around the entire Earth more than 7 times in a single second.
The ultimate speed limit.
Right. Now imagine a very, very small virus. An attosecond is so short that in that amount of time, a beam of light can't even make it across the width of that single tiny virus.
Wait, hold on. Say that again. Light. The cosmic speed limit cannot cross a virus in 1 attosecond.
That's correct. Let's break it down even more. A small virus might be, say, 20 nanometers across. A nanometer is a billionth of a meter, so already that's incredibly small.
Invisible to us.
Completely. But for a photon, which is a particle of light traveling at its breakneck speed, it still takes a measurable amount of time to cross that 20 nanometer distance. And that time is roughly 60 to 70 attoseconds.
Okay, so the time it takes light to cross a germ is about 70 attoseconds.
Roughly, yes. Now consider the events they measured in this experiment. For material like copper, the quantum transition we're talking about, the electron's escape, took about 26 attoseconds.
So the entire process of the electron getting hit, getting excited, and completing its transition happens in less than half the time it takes light to cross a single virus.
Exactly. It's not that the electron is moving faster than light, of course. Nothing does that. But the duration of the event, the time it takes for its entire quantum state, its wave function, to evolve from stuck to free, is shorter than that light crossing time.
That's just absurd. It feels like trying to measure the duration of a single thought, but then scaling that down by a factor of 1 billion.
It gives you a sense of the fundamental clock speed of reality. If you could stretch a single second to be as long as the entire age of the universe, about 13.8 billion years, an attosecond would be just a few seconds in comparison.
Wow. Okay, so that brings us to the next obvious and I imagine very difficult question. If it's happening that fast, how on earth do you measure it? You can't just, click a stopwatch.
You absolutely cannot. And this gets us right to the heart of the problem in this field, what we can call the external clock issue. It's a massive challenge in quantum physics.
The measurement problem.
Yes, a version of it. Professor Hugo Dill, who was the lead on this study, is very clear about this. If you try to bring in any kind of external tool to time the event, say an ultra-fast laser pulse that acts like a flash on a camera, that tool itself is going to interact with the electron you're trying to measure.
It's the classic observer effect, right? By looking at something quantum, you change it.
It's exactly that, but in a very physical, very direct way. It's more than just looking. I think the best analogy is one they hint at in the paper. Imagine you have a tiny thimble full of water, and you want to measure its temperature with perfect accuracy.
Okay.
But the only thermometer you have is a giant industrial one, fresh out of a furnace, glowing red hot.
Right. If I stick that enormous hot poker into my tiny thimble of water, I'm just going to boil the water away.
Precisely. You're not measuring the water's original temperature. You're measuring the temperature of water that you just flash boiled with your tool. The very act of measuring has completely distorted the reality you wanted to observe.
Your measurement created a new reality.
It induced artifacts. That's the technical term for it.
Can you explain what an artifact is in this physics context? Because it makes me think of finding old pottery, not data.
It's a great question. In experimental science, an artifact is any signal in your data that looks like it's a real phenomenon, but it was actually created by your measurement process or your equipment.
So it's a ghost in the machine.
A ghost in the machine. Perfect.
Yeah.
Imagine you're taking a photo of a sprinter at the finish line, but your camera has a really slow shutter and you use a bright flash. When you look at the photo, the sprinter might look blurry, or maybe they look like they have two heads because they moved while the shutter was still open.
And if I didn't know anything about photography, I might publish a paper saying, incredible discovery, humans grow a second head when they run at high speed.
Exactly. You'd be misinterpreting an artifact of the camera as a real biological event. In the quantum world, when you use these intense laser pulses as an external clock, the laser's own electric field starts yanking the electron around. It pushes and pulls on it.
So it's not just a passive observer, it's actively interfering.
Actively. You might measure a certain wobble in the electron's path and say, aha, I've discovered the natural wobble of an escaping electron. But you haven't. You've discovered the wobble caused by your laser. It's an artifact. And Professor Dill's whole point is that any external reference, any outside clock, carries this huge risk of distortion.
And this is even with the amazing technology that won the 2023 Nobel Prize in Physics, which was for generating these attosecond laser pulses. So even those tools are too clumsy, too loud for this kind of work.
They are brilliant for creating the attosecond scale light. They give us access to that world. But for this specific task, measuring the intrinsic time it takes for an electron to evolve on its own, using them as the stopwatch is like using a sledgehammer to perform brain surgery. You need something more subtle.
We needed a stealth mode.
We needed a way to ask the electron how long its journey took without it knowing we were even there.
Okay, so that sets up the conflict perfectly. We need to time a race that's over in the time it takes light to not even cross a virus. But we can't be at the finish line with the stopwatch because just our presence there completely screws up the race. So what do?
Well, if you can't bring a clock to the electron,
You use a clock that's already there.
you use the clock that's already there. This is the core of their breakthrough. The team, led by Hugo Dill and the first author, Fei Guo, they figured out how to use a fundamental property of the electron itself as the internal timing mechanism. And that property is its spin.
Okay, spin. This is one of those quantum terms that we hear all the time, but it's really slippery. Is the electron actually spinning like a tiny basketball on its axis?
It's a great question, and the honest answer is not really. It's not a classical spinning ball, but it has a property that is mathematically identical to angular momentum. It has a magnetic orientation, a sort of north and south pole. For our purposes, the crucial thing is that this spin state can hold information.
It's like a tiny compass needle built into the electron.
That's a very good way to think of it. And when that electron absorbs a photon and starts its prison break out of the material, that compass needle, it moves. The spin state evolves during the journey.
So the spin is like the electron's black box recorder, its flight data recorder, it's logging the trip.
That is a fantastic analogy, yes. Fei Guo, the lead author, says their experiments yield the timescale required for the wave function of the electron to evolve. The final direction of that compass needle, the spin state when it comes out, tells you exactly what happened during the trip.
You mentioned wave function, but just to refresh, that's the mathematical cloud of probabilities that describes the electron, right? It's not a point, it's a field of possibilities.
It is. And this is where it gets really, really weird and interesting. When the photon hits the electron doesn't just, pick one exit door and run through it. This is quantum mechanics.
It does everything at once.
It takes all the doors at once.
Yeah.
It follows several different quantum routes simultaneously. It's in a superposition of all possible paths out of the atom.
That's like something out of a science fiction movie. It takes the highway and the side streets and tunnels under the city all at the same time.
In essence, yes. And each of those different paths has something called a phase. You can think of the phase as the ticking hand on a tiny clock that each version of the electron is carrying. As an electron wave travels along a path, its little clock hand rotates. If it takes a very short, direct path, the hand might only rotate a little bit. If it takes a longer, more convoluted path, the hand rotates a lot more.
And all these different versions of the electron, with their clocks all pointing in different directions, they all meet up at the exit.
They do. And they interfere with each other. This is just like ripples in a pond. If you throw two stones in, the waves spread out and overlap.
Right.
Where two crests meet, you get a bigger wave. That's constructive interference. Where a crest meets a trough, they cancel out and you get flat water. That's destructive interference.
Okay, I'm with you.
The electrons' different paths do the same thing. They all converge, and their phases add up or cancel out. And this final complex interference pattern gets imprinted directly onto the electron's spin. The final direction of that compass needle is the sum of all those spinning clock hands.
Okay, let me try to put this into an analogy and make sure I've got it. It's like, I'm a detective trying to figure out how long a hiker spent in a dense, foggy forest. I can't follow them because my presence would change their path.
Right, you'd scare off the wildlife. They'd take a different route.
Exactly. So instead, I wait for them to come out the other side. And instead of looking at a watch, I look at their shoes. By examining the unique pattern of mud, scuffs, and worn-down tread, the interference pattern from all the little paths they took inside, I can work backwards and calculate exactly how long they must have been walking.
That is an excellent analogy. The wear and tear on the shoes is the final spin state. And by reading that, you can deduce the duration of the journey. The hiker brings their own clock printed on their shoes.
And as Fei Guo said, the method does not require an external reference. There's no outside clock. It's all internal.
It completely removes the risk of those artifacts, of the hot thermometer problem. We aren't imposing a clock on the system. We're learning to read the diary the system wrote itself.
That's brilliant. Okay, so they have the theory. The spin is the clock. But now you need a machine, a device that can actually catch these electrons as they fly out and read that incredibly subtle spin state. The source mentioned an acronym, SARPS.
It does sound a bit like a comic book villain, doesn't it? Kneel before SARPS.
It really does, but it stands for something much more complicated.
It does. It's spin and angle resolved photoemission spectroscopy.
Whoa. Okay, that is a mouthful. Let's break that down piece by piece. Photoemission spectroscopy, that's the part where you use light, photons, to knock electrons out, right?
Correct. That's the core of the technique. Let's just walk through it. First, you need an incredibly powerful and precise light source. For this, they go to a synchrotron facility.
These are those huge circular particle accelerators, building-sized machines.
Exactly. They generate extremely intense beams of light. So, step one, you fire this intense synchrotron light at your material sample.
Step two, the photons hit the electrons, giving them that energy boost for the prison break.
Right, they get excited to a higher energy state. Step three, with enough energy, they are forced to completely leave the material. They get ejected out into a high vacuum chamber.
And this is where SARPS, the machine, is waiting for them.
Yes, and this is the resolved part of the name. As the electrons fly out, the detector measures three key things about each one simultaneously. It measures its final energy, it measures its direction of travel or its angle, and crucially, it measures its spin.
Okay, energy and spin make sense for what we've been talking about, but why the angle? Why does it matter which direction the electron flies off in?
That's a fantastic question, and it's key to the precision of the experiment. The angle tells you about the electron's momentum while it was still inside the crystal. In a material, electrons don't just buzz around randomly like a swarm of bees. They exist in specific energy bands and travel along specific pathways or highways defined by the crystal's structure.
So the exit direction tells you which highway it came from.
Precisely. By measuring the angle, you can trace its trajectory back and say, this electron came from this specific orbital with this specific momentum. It's the difference between hearing the roar of a crowd and being able to pick out a single person's voice and what they were saying. It gives them incredible specificity.
So SARPS is this amazing machine that basically acts like a quantum forensics lab. It catches the escaped electrons, and it figures out how fast they're going, where they came from, and it reads their internal clock.
That's a perfect summary. It's forensic physics. And with those three pieces of data, energy, angle, and spin, they can reconstruct the entire story of that quantum transition.
Amazing. Okay, so we have the method, we have the machine. Now, the experiment itself, they didn't just want to prove they could measure the time, they wanted to test a hypothesis.
This is where it gets really profound. We now have a stopwatch. The next question is, does the racetrack itself affect the lap time? Does the geometry of the material, the stage, affect the performance of the actor?
And to do that, they chose materials with very different atomic shapes.
Yes, they very cleverly picked three classes of materials to represent different dimensionalities, different kinds of symmetry. First up, they used just plain old copper.
The stuff in our pipes and wires.
Exactly. And the reason they chose it is because copper has a very standard, fully three-dimensional crystal structure. It's highly symmetric. The atoms are arranged in a repeating cube-like pattern. You can imagine it as a perfectly built jungle gym that extends forever in all three directions, up, down, left, right, forward, back.
So every atom has neighbors on all sides. It's a very connected 3D world for an electron.
Right. That's our 3D baseline, the jungle gym. Next, they looked at two materials, titanium diselenide, or Ti-C, and titanium ditelluride, TiT.
Definitely more exotic.
These are what we call layered or two-dimensional materials. Think of a perfect stack of infinitely thin sheets of paper or a deck of cards. Within each sheet, the atoms are very strongly bonded together, but the connection between the sheets is very weak.
So an electron can zip around on one sheet really easily, but it's hard for it to jump to the sheet above or below it?
Precisely. For all intents and purposes, the electrons are living in a 2D world. They've gone from a 3D jungle gym to a 2D stack of pancakes. The symmetry has been broken in one of the three dimensions.
Okay, I see the progression. 3D, then 2D. What's next?
Next is a material called copper telluride, or CUTE. And this one has a chain-like structure.
So, like beads on a string.
A perfect analogy. The atoms are arranged in long linear chains, so an electron is basically confined to moving forward or backward along that one-dimensional line. That's a 1D world.
So we have the 3D jungle gym, the 2D pancakes, and the 1D string of beads. The only major variable between them is the geometry, the symmetry of the environment the electron lives in.
And that was the whole point. The hypothesis was, does the shape of the room affect how long it takes the electron to find the exit door?
I really love this experimental design. It's so elegant. It's like you're setting up a race with three identical runners, but one is running across a wide-open ballroom, the second is running down a narrow hallway, and the third is running on a tightrope. And you want to see who gets out the fastest.
And the results were not just clear, they were, I think, quite surprising.
Okay, let's get into the results, because this is where my normal everyday intuition starts to break down. If I'm one of those runners, I might think the tightrope, the 1D chain, would be the fastest. It's the most direct path. No distractions, no side-to-side movement, just go straight.
That would be a perfectly logical assumption in our classical world. But the quantum world, it doesn't play by our rules. The results showed a very clear and opposite pattern. The less symmetry the structure had, the more time the transition took. The simpler the geometry, the slower the event.
Wait, really? The simplest structure is the slowest? That feels completely backwards.
It's profoundly counterintuitive. But the data is unambiguous. Let's just go through the numbers. The fastest transition by far was in the 3D copper, the jungle gem.
Okay, what was the time?
The time for that electron transition was measured to be approximately 26 attoseconds.
26. Okay, that's our baseline. Blisteringly fast.
Right. Now let's go to the 2D layered materials, the stack of pancakes, tailleur on tailleur. The transition time jumped way up. It was in the range of 140 to 175 attoseconds.
Whoa, hang on. From 26 to, let's say, 150, that's what, 5, almost 6 times slower, just from taking away one dimension of movement.
Yes. Just by confining the electrons to flat sheets, the whole process slowed down dramatically. And then, the real shocker, the 1D material, the chain-like copper telluride, the tightrope walker.
What was its time?
It was the slowest of all. The transition time stretched to over 200 attoseconds.
So the tightrope was the slowest. We go from about 26 in 3D to about 150 in 2D and over 200 in 1D. That is a clear trend. But why? Why does being stuck in a simple chain make the electron so much more sluggish than when it's in the complex 3D world of copper? You'd think the jungle gym would be full of obstacles.
It all comes back to those quantum roots we talked about, the wave function and interference. In the highly symmetric 3D copper, the electron has a huge number of possible paths it can take simultaneously. There's a rich network of connections.
So it's like a city with a perfect grid system. Lots of options to get from A to B.
Exactly. And because there are so many available routes, there are more opportunities for the different parts of the wave function to interfere constructively, to build up the necessary oomph to complete the transition quickly. The high symmetry facilitates a very efficient, very rapid evolution of the wave function.
The crowd can move quickly because there are doors and windows open in every direction. There are no bottlenecks.
A great way to put it. Now contrast that with the 1D chain. The electron is stuck on a single track. Its neighbors are only in front of it and behind it. This severe confinement drastically limits the number of quantum pathways available. The interference pattern it can create is much simpler, much more restricted.
So because it has fewer options, it takes longer to build up the right conditions to make the jump.
That's the essence of it, yes. The constraint itself introduces a delay. The accumulated phase, which is our internal clock, it just builds up differently, more slowly. The wave function has to sort of wait longer for the quantum mechanics to align in just the right way for the transition to finalize.
That is so fascinating. We think of complexity creating bureaucracy and slowing things down. But here, the quantum complexity of the 3D structure is what makes it so efficient and fast.
It's the shape of the world the electron lives in. That's what dictates its temporal behavior. The less freedom it has geometrically, the longer it takes to act. Lower symmetry means longer transition times.
This really brings that phrase, geometry meets time, to life. We are literally seeing the physical architecture of a material warping the local flow of time for a quantum particle.
It is, for all practical purposes, a localized time dilation, not caused by gravity like in relativity, but by quantum geometry.
Okay, we've established this incredible counterintuitive result. 3D is fast, 1D is slow. We've clocked the unclockable. Now let's get to the big so what. I can hear people listening and thinking, okay, that's neat physics, but 26 attoseconds versus 200 attoseconds, it's all literally faster than the blink of an eye. Why should I care?
And it's a completely fair question. For our human senses, the difference is zero. But for fundamental physics and for the future of our technology, the difference is absolutely monumental.
Let's start with the big picture, the theoretical side. Professor Dill is quoted as saying, "This work could help us finally understand the role of time in quantum mechanics." That's a huge claim.
It's a massive claim, and I think it's justified. For the better part of a century, there's been this nagging debate. Are quantum jumps truly instantaneous? The early models, the Bohr model of the atom, they depicted them as these magical instant leaps. An electron teleports from orbit A to orbit B. This research provides some of the strongest evidence yet that they are not instantaneous.
It puts a number on it. It kills the instant myth.
It does, and it does something more. It tells us that the duration, that time, is not some fixed universal constant. It's interactive. It depends on the material, on the geometry. This hints at a much, much deeper connection between the fabric of space, the geometry, and the flow of time at the most fundamental level.
It almost sounds like it's echoing general relativity, where massive objects curve space-time, and that curvature is what we feel as gravity, and it also affects time. Clocks tick slower near a black hole.
That's a very sharp insight. It feels like a quantum mechanical parallel to that. Relativity tells us that mass and energy curve space-time, and thus bend the flow of time. This is telling us that quantum geometry, the arrangement of atoms, also bends the flow of time for quantum processes. It might be a crucial clue in the search for a unified theory that can connect the world of gravity with the world of quantum mechanics.
Okay, so philosophically, it's a game changer. What about the practical side, the engineering, the gadgets? How does knowing this let us build better things?
This is where it gets really exciting. Think about where all of our advanced technology is heading. We're moving deeper into the quantum realm. Quantum computing, quantum sensors, quantum cryptography, all of these technologies depend on one thing: the precise control of quantum states.
Controlling qubits, getting electrons to do exactly what you want them to do.
Exactly. Now, if you're building a quantum processor, you are essentially switching these states on and off, or moving an electron from one place to another to represent a piece of information. The speed of that switch, the duration of that transition, becomes a critical design parameter.
And if you've been assuming that switch is instantaneous, but it actually takes 200 attoseconds because you built your device out of a 1D chain-like material, your whole calculation could be off.
Your timing could be completely off. You could get what you called quantum lag. In the field, it could lead to decoherence, where the delicate quantum state just falls apart because you didn't account for that delay. The system gets out of sync with itself.
But now we know that geometry controls timing, so we can use that. We can design materials to have specific clock speeds.
That is the key takeaway. It gives us a brand new knob to turn in material science. It's a design tool. If I need to build a quantum switch that has to operate incredibly fast, I should probably build it using a material with high 3D-like symmetry.
And if I need a process to be a little slower, maybe I need an electron to stay in an excited state for a bit longer, to act as a memory buffer, or to sync up with a slower signal.
Then you might intentionally design your material with a 1D chain-like structure to deliberately stretch out that transition time. You can engineer the timing by engineering the atomic architecture. It's an incredible level of control that we just didn't know we had.
We can build materials that are fast or slow on a quantum level by design.
It also gives us a new way to investigate materials we don't understand yet. Suppose we discover some new exotic superconductor. We can hit it with this SARPS technique and measure the internal timing of its electrons. That timing profile could reveal all sorts of hidden symmetries or strange geometric properties that we couldn't see with any other tool.
It's a diagnostic tool. You can listen to the material's quantum heartbeat to figure out what's going on inside.
A very, very fast heartbeat, but yes.
Okay, so let's try and wrap this all up. We started with this image of a melting quantum clock. We went down to the attosecond scale, a world where light can't even cross a virus.
An almost unimaginable world.
And we learned that you can't time an event there with an external stopwatch because your stopwatch will break the very thing you're trying to measure, the hot thermometer problem.
You have to be clever. You have to find the clock that's already there.
Which turned out to be the electron's own spin, its internal compass needle that records the wear and tear of its journey.
The hiker's shoes.
And then we looked at the big race, the 3D jungle gym of copper versus the 2D pancakes of titanium diselenide versus the 1D tightrope of copper telluride.
And the result was completely counterintuitive.
The simplest path, the 1D tightrope, was by far the slowest. The complex, highly connected 3D world was the fastest. More complexity meant more speed. More simplicity meant more delay.
It's an incredible conclusion. The big lesson here is that time, at this fundamental level, is not an absolute universal river. It's a local phenomenon. Its flow is shaped and dictated by the immediate environment of the particle.
It makes you look at a simple copper wire completely differently. You realize that for the trillions of electrons zipping around inside it, their experience of time, the very rhythm of their existence, is different from the electrons inside the graphite in your pencil.
It just reminds us that our human-scale perception of a steady, ticking clock is just a massive statistical average. Underneath it all, the universe is a symphony of incredibly complex rhythms, speeding up and slowing down based on the local geometry.
Before we sign off, I just want to leave our listeners with one final, bigger thought to chew on. We spent this whole conversation talking about how the geometry of matter dictates the speed of time at the quantum level.
Right.
So let's just zoom out, way out. If the shape of a crystal changes the flow of time for an electron, what if time, as we experience it, is nothing more than an emergent property, a side effect of the overall shape of our universe?
That is the ultimate provocative question, isn't it?
I mean, think about it. We see time as this unstoppable force that carries everything along with it. But this research shows that if you change the geometry, you change the time. What if we could somehow change the geometry of our own environment? Not just a crystal, but the shape of space around us. Could we change the flow of time for ourselves?
General relativity already tells us that a massive object like a black hole does exactly that. It warps geometry so much that time slows to a crawl. But this research hints that maybe you don't need a black hole. Maybe it's a more fundamental principle. Geometry is temporal destiny. If we could ever learn to manipulate the geometry of space itself.
Who knows? Maybe the key to time travel isn't a machine that moves through time. Maybe it's a machine that just reshapes the room you're standing in. And on that note, I think we'll leave it there. Thank you so much for joining us.
Thank you. It was a pleasure. Keep asking questions.
Until next time.